What I want to talk about today is the X-ray spectroscopy of light-induced chemical reactions. I did most of this work as a postdoctoral fellow with Steve Leone, UC Berkeley, Lawrence Berkeley National Lab. So at the very outset, I'd like to thank former colleagues in UC Berkeley, all of our former collaborators listed on the bottom right of the screen. So what we did in Berkeley is we would take a near-infrared laser photon energy very close to an electron volt or so, and we would upconvert these photons all the way to 300 electron volts using a process known as high harmonic generation. So every spike that you see, this is a typical spectrum imaged on a CCD camera. Every spike that you see is a higher order harmonic of the fundamental. And what I want to show you today is that these high harmonic energies, when coupled with time resolved detection, can be a valuable and universal probe of molecular dynamics. So the last few years have seen a huge upsurge in ultrafast X-ray science, where proof of principle experiments are being increasingly and routinely applied to real-world chemical problems riddled with a great deal of complexity. And this has led to the commissioning of new beamlines, upgrading existing beamlines, all moving in the general direction of higher rep rate, brighter flux, and shorter pulses. But tabletop experiments have advanced as well, primarily lured by the so-called water window region. This is a region of the soft X-ray spectrum between 280 electron volts and 550 electron volts, which contains the 1s absorption edges of carbon, nitrogen, and oxygen, which are the fundamental building blocks of life. What happens in this region is that an added advantage is that water is transparent in this region, meaning that you can measure the X-ray spectroscopy of a number of samples in the water window region, all the way from up to 550 electron volt, which is the 1s absorption edge of oxygen. And so the way that tabletop sources do this is using a process known as high harmonic generation. This is a very quick one-slide summary of what this physical process entails. At the heart of it is an ultra-short pulse that is focused in a rare gas medium in a gas cell, shown here on the right. And a blown up view of this is the microscopic view of HAG, which is understood from a semi-classical three-step model. And the intense part of the pulse, labeled B, distorts the Coulomb potential of the atom, as a result of which an electron tunnel ionizes, and it's launched into the continuum. It then propagates and accelerates in the field. And finally, when the laser field reverses sign and crosses zero, there is a finite probability of recombination with the parent ion. And if recombination happens, then it can release all of the energy that it acquired in the field as a short pulse, short pulse of light in the extreme ultraviolet or soft X-ray. One of the very few equations that I will show in the talk today is the energy cutoff for high harmonic generation. Usually it's given by a sum of the ionization potential, which can be tuned by changing the rare gas in the HAG target cell, all the way from helium to xenon. There's another factor, which is the ponderomotive energy. This is the mean kinetic energy of the electron in the field. And this scales linearly with the intensity of the pulse and quadratically with the wavelength of the pulse, meaning that with a combination of factors such as the intensity, the wavelength, and the choice of the rare gas, one can tune the photon energies of high harmonic generation. So these are the three parameters that outline the next graph. What you see here is a plot of all the leading groups in the field who made high order harmonics in the water window and beyond before we got interested in the problem in 2014. So this is not an updated slide. This is before 2014. To quickly walk you through this plot, what you see on the Z-axis is the photon energy. So these are the highest photon energies ever made on a tabletop source. On the X and Y are the phase matching conditions that were sampled. Okay, so a couple of things to note here is that high harmonic generation, first of all, is a very inefficient process, more so at these higher photon energies. And so what needs to be done to ensure phase matching and get a bright enough flux is that first the HAG target cell is packed with several atmospheres of gas pressure, as opposed to a few tens to hundreds of torr below 100 electron volts. Okay, and the second thing to mention is that usually you'd have to go to longer driving wavelengths. So a titanium sapphire output is not utilized anymore at these higher energies. Usually it's going to be a longer driving wavelength laser. The record 1.6 keV energy that has been generated, that's from the Captain Marine group, is clearly skewing this plot. But what you see right away is a flurry of activity in the water window region right there, because there's a lot of interest in doing spectroscopy in that region. But getting to these high energies is not easy. It comes with a price to pay, and the price you pay is the drop in flux. So what you see on this slide is it's pretty much state-of-the-art 2014 Captain Marine, where as the energy increases from 20 to 200 electron volts on the x-axis, you can see that the photon flux comes plummeting down an order, 2 orders of magnitude, such that a couple of questions that were open questions in the field at the time that I was starting out in UC Berkeley were A, will it be possible to measure the X-ray, a static X-ray absorption spectrum of a carbon film or a carbon-containing molecule? And B, more importantly, will it be possible to measure dynamics of the carbon KH of an organic molecule, knowing that most organic chromophores will not absorb more than, it's given their UV absorption cross sections, it's difficult to excite more than 20%, 20 to 25% of the molecules in the probe volume. So to answer some of these questions, we made the first ultrashort 300 eV pulses on a tabletop source in Berkeley in the Leone labs in late 2015. And we use this to study a number of photochemical reactions. This is a closer view of the high harmonic spectra that we would make in Berkeley. So what you see here is that the spectrum is tunable from 30 electron volts all the way to 300 electron volts, where by changing the phase matching here in the inset, you can see a combination of different HAG target gas, pressures, as well as driving laser wavelengths. We can tune the high harmonic spectrum across this range. These ultrashort X-ray pulses, they are broadband. These are energy tunable. Most importantly, they provide access to multiple absorption edges. Some of these elements highlighted here on top, promising to be a very valuable universal probe of molecular dynamics. A couple of parameters for those of you who are interested, that the spectral resolution for XUV beamline, meaning less than about 100 eV or so for this tabletop setup, was characterized as 25 millielectron volt for the spectral resolution, and under 100 femtoseconds, about 70 femtoseconds for the temporal resolution. Closer to the carbon K edge, we had a time resolution of about 90 femtoseconds, spectral resolution of 300 MeV, which we did not work too hard on this number, but this can be worked upon further. And what we are interested to do, we are organic photochemists, and so we are inspired by carbon as an element in the periodic table, has very unique property of linking very easily to other carbon atoms. This is a property known as catenation, which allows carbon to form extended chains or extended rings. If these are pure, only composed of carbon and hydrogen, these would be hydrocarbon rings, as shown here on the left. But on the right here is how nature incorporates heteroatoms such as nitrogen or oxygen or sulfur to trigger charge transfer in functional matter. Okay, so what you see here is a group of macrocyclic cages known as porphyrins or nuclear bases or natural products, which heavily incorporate heteroatoms in the ring, and these would be heterocyclic rings. And ring opening of these hydrocarbons or heterocyclic rings, these are of interest, both from a biological and as well as a technological point of view. So on the left here, you see molecule 7-dehydrocholesterol, which breaks this pink bond in the presence of sunlight, and this underlies the synthesis of vitamin D in your skin. On the right, you see similarly another bond here highlighted in pink, which is in a spiropyran molecule. This molecule changes color in the presence of sunlight, and so this is implicated in functioning as molecular switches and such. But how does one think about chemical reactivity in organic rings? And it really rises, the concept emerges from first principles chemical bonding. And the way I like to introduce this is from a familiar picture of the periodic table, where on the left you have the S group of elements, the S block of elements, which have the outermost shell would be an S orbital. On the right, you have the P group of orbitals, the P block. And so chemical bonding emerges when you start to combine these atomic orbitals to form molecular orbitals. And you can think of this as a linear combination of atomic orbitals illustrated here on the left, where you have two atomic orbitals, phi1 and phi2, which then interact, and this resonance interaction leads to the splitting in energy between the symmetric and the antisymmetric combinations. Another way of looking at this picture would be the overlap and mixing of the orbitals, where you can see that the in-phase or the outer-phase overlap of two p orbitals can lead to an increased electron density in the internuclear space, or a depleted electron density in the internuclear space. And this would be the sigma and the sigma star. So this sigma bonding and sigma antibonding orbitals in case of the head-on overlap of two p orbitals. And the same principle for the side-on or lateral overlap of two p orbitals, giving rise to a pi bonding or a pi star antibonding orbital. And so one can do this for a diatomic here, for instance, where you take two p orbitals, there is this stabilization energy due to the interaction energy of the two p orbitals, and then it prefers to have a bonding equilibrium configuration here, giving rise to a certain well depth for this ground state for the molecule. And one can do the same for higher excited state electronic configurations as well, shown in yellow, which is a dissociative state, or in purple, which is a bound electronic state, where the leading electronic configuration in the molecule emerges as a useful shorthand notation for the electronic state. So pi star would mean that there's a single electron each in the pi and the pi star orbitals. This could be singlet or triplet. Pi sigma star would mean there's a single electron in the pi and sigma star. Okay. And for the last 4 or 5 years, I have been looking at the chemistry of excited electronic states. I think this is a great way of performing photochemical bond activation. I've been working in the areas of simple unimolecular ring opening type of reactions, all the way to complex sequential multi-step photocatalytic redox, photoredox reactions in solution. And the main motivation is that this is a clean, targeted chemical reactions can be targeted, and that this is central to a number of fields, including photosynthesis, photoredox catalysis, and photoelectrochemistry. For the talk today, I'm going to focus on time-resolved X-ray absorption spectroscopy as the methodology, where the time delay between the pump and probe pulses will map out the reaction coordinate. And the X-ray absorption spectroscopy will inform the peak-to-peak energy separation. And so this, by following the position of the peaks in the near edge part of the spectrum, one can infer the changes in the valence electronic structure in the chemical reaction. So this is a quick schematic of the pump probe method that we use. On the left, what you see here is in black is the ground electronic state. In colors are the excited electronic states. This would be a bond dissociation. This would be a bond isomerization reaction. typically, we launch these excited state photochemistry using an optical pulse, ultra-short optical pulse. For the experiments that I'll show today, this will be 266 nanometer pulse, which is conveniently generated as a third harmonic of the of a titanium sapphire laser. And then this is the time zero for the reaction. And then you can bring in an X-ray pulse that is delayed in time. And the X-ray pulse can project the core electrons into the changing valence electrons, the changing valence orbitals of the molecules. And this it can do from both the ground state reactant all the way to the photo product and the entire transition state region in between. So we think of this as a very useful universal probe of molecular dynamics. What does a typical X-ray absorption spectrum look like? This is for the benefit of those of you who don't read a lot of literature on X-ray spectroscopy. This is illustrated here for a diatomic, but equally well applies to polyatomics as well. While the valence orbitals, sigma pi, sigma star, pi star, etc., that are introduced earlier, while these orbitals are delocalized over the entire nuclear framework, the core, which would be the 1s or the 2s or 2p type of orbitals, these are strictly localized. And so an X-ray absorption spectrum as a function of the increasing energy contains a number of these fine structures in the near edge, what's known as the near edge, and these are bound core to valence transitions. Okay. In the extended edge, there are a number of oscillations that are due to interferences of the outgoing, the scattered photoelectron, reporting on coordination numbers, bonding geometry, etc., which we will not go into. For the purposes of today's talk, we will focus on NextSAFs because it is element specific. It's an element specific technique, meaning what you see here is the X-ray absorption spectrum of a very complicated polymer shown here in the inset. But regardless of the complexity of the molecule, the X-ray absorption spectrum bunches itself into these neat absorption edges of the constituent elements, which are separated in energy by several tens to 100 electron volts. So it's element specific. Intrinsically, it's also orbital specific. So what you're looking at here is the X-ray absorption spectrum of a carbon nitride film composed of carbons and nitrogen atoms. And what you see here is that not only is the 1s pi star very different in energy as well as shape from the 1s sigma star, but that this information is also sort of duplicated, imprinted in the nitrogen edge as well. So one can focus on these different sites in a carbon nitride film. And finally, it is chemical site specific, meaning that here you're looking at the same 1s to pi star core to valence resonance in benzoic acid and parahydroxybenzoic acid, where depending on whether you're looking at an olefinic carbon in blue or an alkoxy carbon in green or a carboxyl carbon in red, the 1s to pi star core to valence energies can be shifted by about 1 to 2 electron volts of energy. So this technique is also chemical site specific, and when this happens, these shifts are known as chemical shifts. Finally, as in any spectroscopy, in X-ray absorption spectroscopy, we often think about selection rules and we think about oscillator strengths. A question that I often get asked is, how close are you to breaking the electric dipole approximation at these energies? The answer is not at all. So we are definitely, even at the carbon K edge, the selection rules are governed by the electric dipole selection rules. And in fact, these rules are good up and until the hard X-ray region at about 7 keV or so, if you have to measure say, for example, the iron K edge at a free electron laser. So these are the selection rules. These are going to be the same as for any electronic absorption spectroscopy. On the right is the sort of the expectations for the intensity patterns, and something that's going to be relatively less important for today's talk because we are doing K spectroscopy, so there's no spin orbit coupling. But in general, for all spectroscopies that does not involve the K edge, so L and higher, one has to worry about spin orbit splitting as well. and that the oscillator strengths are dictated by Fermi's golden rule, which means that at lower photon energies, we have increasing transition strengths. The way the experiment works is that I showed a brief schematic before. So we take an ultra-short pulse at 800 nanometer or 1320 nanometer for the experiments that I will describe shortly, about 1.8 millijoule per pulse at 1 kilohertz rep rate. This is focused in a gas cell filled with, say, helium at 780 torr. At the entrance of this is an IR window. At the exit is a Teflon disc. We focus very close to the Teflon disc to about 10 to the 13 or 14 watt per centimeter squared. This drills a hole and out come the harmonics. These harmonics get filtered by an aluminum foil, 100 nanometers thick, because this is a diverging beam, it's refocused into a sample cell. There's a titanium foil, 50 nanometers thick, that is preventing the backflow of the gas vapor onto the toroidal mirror. In a parallel arm, we bring a 266 nanometer pulse, which is generated as a third harmonic of the titanium sapphire laser that is routed by a variable delay stage that controls the pump probe time delay. This is then overlapped onto the same gas cell, which contains a 200 micron hole through which the vapors are made to flow. And this is happening at a very shallow crossing angle of 1 degree or so. At this point, the UV, the transmitted UV is blocked, the transmitted X-ray goes through, and this happens because of a titanium foil 100 nanometers thick. This is then dispersed by a grating on a CCD chip showing high harmonic spectra that I showed in a previous slide. Okay, and so using these high harmonic spectra, we've applied these X-rays to study a host of photochemical reactions, really. So what you see here on the right are the sort of molecules that we've looked at. On the left are these series of colored dots, which are telling you which energies were used to probe these reactions. Okay, so for today, I'm going to focus on these 3 reactions in black, which is 2 ring opening reactions. All of these were done at the carbon K edge at 284 electron volts. But I still wanted to put this slide up to sort of impress upon you the universality of the method. In particular, for A-band photodissociation of halogenated alkanes, we were able to study these reactions simultaneously, exciting the iodine 4D electrons at 45 eV. So that's the iodine NH, the bromine MH, which is the 3D electrons of bromine at close to 70 electron volts, the chlorine LH close to 200 electron volts for chlorine 2s 2p electrons, and finally the carbon KH at 284 electron volts. So moving on to the pericyclic ring opening reaction of cyclohexadiene. This is a very simple reaction as a function of the reaction coordinate, which in this case is a C1-C6 bond distance. So we shine 266 on this molecule, 266 nanometer light on this molecule, and how it responds is that it breaks open, and the reaction coordinate here is a C1-C6 bond distance. You can see that the end-to-end distance increases as a function of this line or this arrow. The potential energy surface for this reaction is very well known. And so what is known is that at 266 nanometer, we populate the 1B, which is a pi star excited state. Okay. And then there is very fast departure of the Frank-Condon, from the Frank-Condon excited area. So this configuration, there's very fast departure of the wave packet, at which point it crosses the 2A dark state. And here it encounters an excited state minimum, the so-called pericyclic minimum. And as this wave packet bounces back and forth, it can bifurcate either into the ring closed form, cyclohexadiene, or the ring open form, hexatriene, both with very high levels of internal vibrational excitation. Now, in X-ray spectroscopy, what we are really sensitive to is the electronic structure. And so what I'm showing here is the electronic structure at representative locations on the potential NG surface in these green boxes. And so in the ground state of cyclohexadiene, we have a 2 pi HOMO, or highest occupied molecular orbital. We have a 1 pi star LUMO, or lowest unoccupied molecular orbital. In the 1B state, which is the photoexcited state, this is a pi star excited state, meaning that an electron has been promoted from the 2 pi HOMO to the 1 pi star LUMO. As this electron, or as this molecule evolves into the pericyclic minimum, in the vicinity of this, the pi star energy gap closes in, as you would expect from the closing gap of the ground state and the excited state potential energy curves. And in this region, the molecule has significant levels of double excitation character. And finally, in the ring open form, where the C1-C6 bond distance has increased, and we have the isomers of hexatriene, we've recovered a 2 pi homo and a 1 pi star LUMO, meaning the electronic structure for this in the open form is very similar to the electronic structure in the closed form. We have the same pi star homo and LUMO orbitals. So how does this information get imprinted on X-ray absorption spectra? Okay, so what I'm showing here are calculations of the X-ray absorption spectra averaged over 116 trajectories for this reaction. And so what you see here is in black is the ground state absorption spectrum. So the first peak here at 284 electron volts is excitation of a 1s carbon electron into the LUMO, the lowest unoccupied 1 pi star, which is this first peak here, and successively to the LUMO plus 1, 2 pi star, LUMO plus 2, and so on and so forth. Okay. For the purposes of today's talk, I will be focusing mainly on the 1s 1 pi star peak, which is this first peak at about 284.2 electron volts. And then what you see here in the 1B state is the spectrum in red, and just as a comparison, I still have the spectrum in black, which is the ground state cyclohexadiene. What's happening here is that the optical pulse has initiated a pi star excitation, meaning that the LUMO is now partially occupied, and so the oscillator strength of this peak drops. And at the same time, there's a vacancy created in the 2 pi HOMO, as a result of which there's a new transition expected in the pre-edge region above 280 electron volts. As the energy levels sort of merge, collapse into near degeneracy in the vicinity of the pericyclic minimum, the pi star separation reduces, and this is what you see here as well. So the pi star separation has come down, indicating that in the vicinity of the pericyclic minimum, these two orbitals are significantly mixed. They have a mixed character. And finally, in the ring open form, where the electronic structure was very similar to the electronic structure in the ring closed form, in blue, we find that the hexatriene spectrum, this is for a combination, this is for a mixture of isomers of hexatriene, we find that the X-ray absorption spectrum is very similar to what is expected for cyclohexadiene. Now, this is expected, of course, even though the point I want to make here, emphasize here, is that even though nuclear structure-wise, there's a big change in the, from the ring closed form to the ring open form, X-ray absorption spectroscopy is sensitive only to the electronic structures. Okay, so if the electronic structures are similar, so will be the X-ray absorption spectrum. Do note here that the blue spectrum appears in slightly increased oscillator strength for this peak, and this is going to be important in an assignment later on. So with that introduction of cyclohexadiene, I want to show the ground state X-ray absorption spectrum. Here in the solid black line connecting the black dots is the experiment. The solid gray is the theory that I just discussed. And most of this discussion will focus on the first peak labeled peak A, which is, as you will recall, the 1s to 1 pi star transition in this molecule. Okay, this is the 1s to 2 pi star. So this is the LUMO plus 1 plus some contribution from the 1s sigma star as well. Okay, but once again, I will be focusing on this molecule, on this peak mostly. How long does it take to measure such a spectrum? This is typically about 64 images, CCD images, about 100 laser pulses per image. So under 2 seconds, we can measure this signal to noise ratio in our apparatus. This slide and the following two are arranged as pump probe time delay, the electronic configuration in the green box, the theory that I've just walked you through, and the comparison with the experiment, which I'm showing for the first time. Okay, so in the first about 0 to 40 femtoseconds after the reaction is initiated, what we expected, this would be the 1b pi star excited state. And so what we expected peak A to come down because the 1 pi star LUMO is now partially occupied. And this is what we see as well. So this comes down in intensity. And because our pulses are kind of long, we have about 100 femtosecond pulses probing this reaction. We don't exactly see a clear peak here, but rather a broadening and continued absorption to the red side of this peak. Between 90 to 130 femtoseconds, what we can see is that you recall that in the vicinity of the pericyclic minimum, there was sort of collapse of the two energy levels into near degeneracy, and this reflected as a closing gap of these two resonances. And here we can clearly identify between 90 and 130 femtoseconds. We clearly identify this peak close to 282 electron volts, which is indicative of the heavy mixing of the frontier molecular orbitals in this state. Finally, between 350 and 500 femtoseconds, when the reaction is complete, we expected not to see many changes because, as I mentioned, the electronic structure for hexatriene is very similar to ground state hexadiene. Both have pi HOMO and pi star LUMO orbitals. So what you see here is in black. This was the theory for cyclohexadiene. In blue was the theory for hexatriene, vibrationally excited hexatriene. And what we see in the experiment is, of course, some broadening from the internal energy in the molecules, a slight redshift, and this broadening on the red edge. And this is where a very critical referee asked us, looking at the blue spectrum and the black, how can you say that the ring has opened? And so this question is a very valid question. It forced us to think harder. If there wasn't 50, 80 years of work on cyclohexadiene ring opening, if we were to study this molecule for the first time, how would we look at the spectrum in black and the spectrum in blue and be able to say if the ring has opened or not? And so this inspired us to think a little bit harder and do some more calculations. I will not discuss the details of the calculations, but what I do want to discuss is that we argued that even in the limit that all the molecules come back to the closed ring form, as you'd imagine, this would lead to vibrationally excited cyclohexadiene. More Frank-Condon transitions would open up, leading to a broadening of the peak and a strict decrease in the amplitude of the peak. So this is also captured in our non-adiabatic molecular dynamics simulations, where you see that the brown spectrum is for vibrationally excited closed cyclohexadiene, and so this peak should drop in intensity, meaning that this increase in the oscillator strength that we observe in the experiment between 350 to 550 femtoseconds is indicative of the ring opening reaction. And then we were able to compare the oscillator strengths with computed oscillator strengths for this reaction and arrive at a branching ratio of about 60 to 40, 60 being in favor of the ring opening reaction. So this is the ultrafast ring opening in cyclohexadiene deconstructed. What you see here are the key photo product, the ground state reactant, and the intermediate kinetics line out traces, where going from the bottom, this is the rise in the 1s pi star hexatriene resonance at 284.2 electron volts. At the top, you see this is the depletion of the cyclohexadiene 1s pi star resonance at 284.5 electron volts, which recovers, and this is because of the overlap between the two peaks at 284.2 and 284.5 electron volts. But crucially, what we see here is we identify a transient at 282.2 electron volts, which rises in. It's sort of delayed with respect to the depletion of the cyclohexadiene by about 60 femtoseconds and decays with a time constant of 110 femtoseconds. This is indicative of the valence electronic structure being a very mixed pi star state in the vicinity of the pericyclic minimum. An open question for us at the time that we were doing these experiments, writing up the paper and thinking about the results, is about product isomerization in the ground state. So what is going on in this area right here is if that's a question for you, it's good to be aware of the limitations of a technique, and I think this is one of the questions that I would not be using soft X-ray absorption spectroscopy to answer. In particular, time-resolved hard X-ray scattering or time-resolved scattering methods are more valuable. And for those of you who are interested in what's going on in this region, I would like to direct you to this paper that came out of LCLS, which used ultrafast electron diffraction as a probe of the C1, C6 end-to-end distances. I would now like to compare between two ring opening reactions at 266. Jerry, I have a question on this slide. Yeah,
okay, all right, thank you.
Yeah, it's coming up, thank you. And so wanted to quickly compare between two ring opening reactions. So I've showed you one, which is a parent hydrocarbon on the left that undergoes a carbon-carbon bond fission. On the right is a new molecule just coming up, which is a carbon heteroatom bond fission. Before I go to the details of this, questions, please.
Great. Okay. Yes, there definitely are questions. Josh, would you like to start?
Yeah. Hi, Aditi.
Hi, Josh.
This is really fun stuff. You know that, like, so you showed at the beginning the energy ranges of the different harmonic sources from, like, the 800 to the 1.3 micron, and you showed that with a normalized intensity. If you did not normalize that, how does the actual flux compare in the X-ray region versus the XUV region, and what's the stability between the two?
Yeah, so yeah, those are both excellent questions, Josh. So first of all, I plotted those on a normalized intensity scale, so it's easy for folks to compare right away. As far as the absolute, on this plot, it would be about 1/8 to 1/10 lower, okay, for the for 300 eV harmonics, okay. The phase matching conditions are slightly different, are very different, in fact, for both ends. And as you know, that the reflectivity of the optics, the quantum efficiency of the detector, the thickness of the metal foils we use, they all change. So a strict comparison for this plot is not going to be valid, but we did not measure, but we estimated the photon flux that we had given, the number of optics or the number of filters and the efficiency of the detector. And looking at those estimations, the numbers that I have in mind are 10 to the 8 photons per pulse in the below 100 eV range, 10 to the 5 near 300 eV. Okay.
It does sound like if you're getting a ground state spectrum in 2 seconds over that whole range, having more photons wouldn't really help you. You're certainly for gas phase reactions, you're not photon limited.
Not for the static spectrum, Josh, but for time resolved, it makes a lot of difference. So just the cyclohexadiene experiments that I showed you so far, at this time, these were the first experiments we did, and then we changed the semi-infinite gas cell that we were using. We used a differentially pumped gas cell that allowed us to step up the gas pressures significantly, leading to a doubling of the flux. And I recall that made the experiments a level easier. The time resolved experiments, a tad bit easier. Thank you.
Ethan, you have a question?
Yeah, so for this ring opening reaction, are there differences between the speeds and efficiencies for differently sized rings? Like, say I had a 5-membered ring or a 7-membered ring.
Mm-hmm.
Speed or efficiency different for this kind of opening reaction?
What people have studied is the effect of substitutions. And so if you had methyl, for example, substitutions along the ring. What could change is the ground state isomerization timescales could be different, because that involves a significant rotation and torsion of the end groups right here. But as far as the ring opening reaction itself, that sort of depends on the gradient of the excited state potential. So as long as that is unaltered, it will not change a lot from changing the size of the rings. But yes, methyl substitutions and other chemical substitutions, which create an inertia, if you will, that can affect significantly the isomerization in the ground state.
Very good. A couple of more technical questions. When you're doing the pump probe experiment, roughly what mole fraction of the gas molecules in your sample cell become photoexcited?
Right. So I think we estimate that for cyclohexadiene. I think I have to remember this. So what we did was we estimated the probe volume given our 266 nanometer focusing conditions, applied the known absorption cross section for cyclohexadiene at 266 nanometer, estimated the number density of the molecules in the gas jet, in our sample cell, and arrived at close to maybe 18% excitation for cyclohexadiene. Maybe 13% excitation is what we said.
Okay, but that's
but it
actually
can change
pretty,
a little bit, but it is unestimated.
That's pretty favorable on the scale of time resolved studies with hard X-rays. This is great.
Yes.
Other question is what typically, two somewhat related questions. What's the typical size of your edge step? And also, how do you extract the transient part in these experiments where only a portion of the molecules are excited?
Right. So typically, people who work with solid state thin films or solid state samples will be doing a lot of background fitting to get the ionization response. This, as you see, some of the spectra. Let me just go back to here, maybe. So this is really a very simple. So this would be cyclohexadiene, just the vapors of the molecules flowing in the sample cell volume. Let's say a number density of 10 to the 17 molecules per cc would give an absorbance of 0.6 OD. Okay, so that this is easily achievable given molecules or samples which have a vapor pressure close to cyclohexadiene or cyclohexadiene type of molecules. A couple of other experiments that I will show you, Jerry, will also have the same absorbance level, so 0.5 or 0.6 in the ground state X-ray absorption spectrum. Typically, because we do 10 to 20% excitation, we will see about 10 to 20% of these signals, meaning the delta absorbance in milli-OD will drop to, say, 20 to 30 milli-OD for the strongest features.
Very good. You should continue, please.
Okay, great. Let's go back to where I stopped, and this would be a comparison of two ring opening reactions. So on the left is a pure hydrocarbon, on the right is a heterocyclic ring, which is furfural. So this is a 5-membered furan ring with an aldehyde group at the second position. Okay. So in the first case, this is a carbon-carbon bond fission. In the second case, this is a carbon heteroatom, meaning a carbon-oxygen bond fission. Convenient starting point is always the potential energy diagram. So the left, I've already discussed before. What I will do for this case, because I'm running out of time, is just discuss the similarities and the differences between the two. Okay, the similarity is that the initial 266 nanometer excitation populates a pi star excited state. There is fast departure of the molecule from Frank-on and excited region, after which it crosses with the pi sigma star state. Okay, this is a repulsive state, meaning that an electron is transferred from the pi star antibonding to a sigma star antibonding orbital, which is antibonding along the CO bond. And so this leads to a cleavage of the CO bond right here and formation of a carbene or a free radical intermediate species. Once again, in X-ray absorption spectroscopy, what we are really sensitive to is the electronic structure. And so on the left, whereas it was not very easy to discriminate between hexadiene, cyclohexadiene ring closed and hexatriene ring open, because both of them had frontier pi star orbitals. On the right here, we will see what implications populating a 2p more atomic-like orbital has in comparison to a pi star molecular orbital. Okay. So on the top here is the ground state X-ray absorption spectrum, comparing the two. On the left is the 1s pi star in hexadiene, which I've already discussed at 284.5 electron volts. You can see already that the 1s pi star transition in furfural splits into two peaks. And this is the point about chemical shifts that I made earlier. So the carbon atoms that are directly bonded to the oxygen are now shifted to a higher transition energy compared to the carbons that are directly bonded to carbon atoms. So this is chemical shift in X-ray spectroscopy and can be a very valuable probe. What happens when we shine light on these molecules? So this is a false color map of the two. What you have on the x-axis is the photon energy. On the y-axis is the pump probe time delay. Black blue is absorption, black blue is ground state depletion, yellow, orange, red is absorption. So what you see right away is depletion of the parent peaks, the 1s pi star resonance in both species. And so this is because we are photochemically exciting the molecule. On the left, we had a close line 1s pi star resonance in cyclohexadiene at 284.2 electron volts. That was very similar in spectrum-wise to the cyclohexadiene molecule. And what we managed to identify in this case was really the delayed rise and the decay of the wave packet in the vicinity of the pericyclic minimum, which had very mixed 2 pi 1 pi star character. On the right here, however, because the photochemical product has a 2p atomic-like or a frontier orbital, this is directly manifested as a 2 EV shift in the rise of this photochemical radical product. Okay, so meaning that ultrafast ring opening happens in furfural on a 350 femtosecond time scale. And so what does this tell us beyond the ring opening or the ring closing timescales? What new science have we learned? Just want to quickly go over a perspective that some former colleagues at the University of Bristol offered. So Mike Ashfold and co-workers wrote this perspective in JPC letters where they said that experimental studies of ring opening are largely in their infancy. The challenges are substantial. And without subsequent collision relaxation, the measurement and assignment of spectra of the ring open species are likely to be challenging. So in these cases, about ring opening reactions in hydrocarbons and heterocyclic rings, we have taken a tiny step forward in defeating some of these challenges in studying ring opening. Okay, but a lot remains to be done. In particular, what about nuclear structural dynamics? To illustrate this case further, I showed you just one side of the problem, just the ring opening coordinate for furfural. It turns out there's an orthogonal coordinate, which is the ring puckering coordinate. In this case, there is no crossing with the pi sigma star state, okay? So here the photoexcited molecule evolves on the initially excited pi star state, undergoes a direct conical intersection with the ground state that safely deposits the molecule back in the ring closed form. Okay, and the structure of the molecule at this conical intersection is distorted, which is called a puckered ring structure. This is not normal mode really. What this is a severely distorted structure with this H atom strongly bent out of plane and this oxygen atom also lying out of plane. And at the time that I was thinking about these results and writing the paper, We made some comments about not being able to discriminate between the ring opening and the ring puckering coordinates in our paper, but at the same time, it got me thinking about what will it take for experiments to be able to tease out these tiny details, these subtle details, and I was very happy to read this paper last year from, again, an ultrafast electron diffraction experiment emerging from SLAC, where they were able to unambiguously detect a ring puckered structure, not in this molecule, but also a heterocyclic ring, which is pyridine. So more details in this paper, which I will not discuss today. So the point is really that complementary experiments are going to be important going forward. Spectroscopy is just one side, which can do quite a few things well, but to look at end-to-end bond distances, time-resolved scattering probes, such as the papers shown on the right, are going to be the way forward. Just want to switch gears and quickly walk through an ultrafast intersystem crossing in this molecule acetylacetone. So this molecule, it turns out you can buy from Sigma Aldrich in a bottle. It comes in a liquid, which is the diketo form. When you pass this in the gas phase, it refers to what is known as the tautomer, which is the enol form, because it's stabilized by an intramolecular OH hydrogen bond. Okay. So what was known about this molecule was that when you excite this at 266 nanometer, it loses a hydroxyl radical. This is a hydroxyl radical elimination reaction, and that this happens on a 250 picosecond time scale is what this JPCA paper told us. That multiple electronic states are involved. At least 2 singlets and 2 triplets are involved. And what was known from a time-resolved photoemission spectroscopy experiment was that there's an ultrafast internal conversion S2 to S1 happening on a 1.4 picosecond time scale. What was unknown was if the triplets are involved at all, and if yes, what is the intersystem crossing time scale? This is the ground state static absorption spectrum of acetylacetone, where again in black line connecting the black dots is the experiment. Solid gray is this theory. What I'm showing you for the first time now are these colored sticks. And the sticks become important now because of chemical shifts in the presence of oxygen atoms. In particular, the blue and the green carbon atoms appear at a higher energy than the red, which is directly bonded to carbon. Okay, and this particular peak right here at 284 eV is a unique signature of the enol form. Turns out if the molecule was in the diketo form, the first transition you would see would be at 286 eV. Okay, so C3 is then chemically shifted from carbon 2 and carbon 4 by about 2 electron volts. When we shine 266 nanometer on this molecule and look for changes in the near edge region, in all of these spectra, the gray trace is before so this is negative time delays, meaning pump arrives later, and so nothing will happen. This is a reference for all practical purposes. Okay, so what we see early on is depletion of the ground state peak, formation of these group of peaks 3, 4, and 6. As these peaks begin to decay, you can see that there's a new peak here. There's a slight red shift and the appearance of a new feature. And finally, most prominently, we see these 2 peaks in the spectrum. Of course, there's a lot going on. So what we did here was a global fit to a 2-state sequential model in this case, which gave us the decay of the singlets, the S2 and S1, which we cannot again discriminate in these experiments, but the rise of a triplet on a 1.5 picosecond time scale, which is very remarkable for an organic molecule of this size. Okay. I want to take a minute here and just explain the significance of this as I perceive it. Okay, so it turns out that you have a host of X-ray absorption, X-ray emission studies, which will show you differences in peak absorption or the location of the peaks for different spin states of the molecule or the metal center, or whatever it is. But the question remains that X-ray absorption is, of course, not directly sensitive to spin states. Okay, so what here I'm trying to propose X-ray absorption as a method of detecting triplets through indirectly, because conservation of angular momentum requires, so imposes certain rules on the changing electronic character. To explain this, what I want to draw your attention to are the peaks that lie below 284 electron volts. Okay, so these are the 1s to pi resonances in the molecule. And it turns out that when singlet and triplet kind of intersystem crossing occurs, because of the change in the spin, it means that the orbital angular, there must be an unit change in the orbital angular momentum. This means that it automatically imposes certain selection rules on the electronic character of the changing states. Okay, so meaning the horizontal ones, pi star to n pi star, would be allowed, but not the diagonal ones that preserve the electronic character. And so, looking at just the pi star region of the spectra for the S2 and the T1, you can see because this is pi star and because this is probing the carbon KH transitions, there is reasonable amount of activity in the 1s to pi resonances here. But for the n pi star singlet and the n pi star triplet, these regions are inactive. And this is because a non-bonding orbital is located on the oxygen atom. Okay, so looking at these features, we can say that there's an S2 to S1 internal conversion in the molecule, followed by a picosecond time constant for the triplet state. So it goes from S2 to S1 and T1. And although this is X-ray absorption spectroscopy is not directly sensitive to the spin states, going by the conservation of orbital angular momentum, or conservation of angular momentum rules, which go by the name of L-Sides rules in organic photochemistry, I think this can emerge as a way to look at singlet triplet spin change in general in organic molecules. In 2 minutes, I want to sort of defend the emphatic claim that I made about X-ray absorption spectroscopy being a universal probe.
Skip the questions for right now. We'll hold them for the end, and you should continue.
Sure. So then, this brief background here. When I was writing this review with Steve, thinking about the results more and more, it convinced me that X-ray absorption spectroscopy could be a universal probe of photoinduced molecular dynamics. And then a very careful and critical reviewer commented that it's okay to call it a new probe or a novel probe, but you must not call it a universal probe because these spectra are governed by dipole selection rules. Okay, so they do not agree with calling it a universal probe. So what I want to end this talk with are two reasons that I made to defend the use of universal that led to the retention of universal in the title. The first being that it's true that we are bound by dipole selection rules. That is not necessarily a disadvantage. In fact, what we've shown is that it's possible, even using a tabletop source, to tune to multiple absorption edges in a molecule such as dimethyl disulfide or CH2ICl, which has both carbon and sulfur on the left molecule, for instance. And so when we look at the X-ray absorption spectrum here, in the bottom panels are the delta absorbance traces, which we directly measure, and the tops are the ground state and the photo products, which are reconstructed in black and blue respectively. What you see here are distinct, the sulfur L1, L2, 3 edges, and the carbon KH here in gray. And we are able to look at each of these regions specifically and not going through the details, especially at the sulfur L1 edge. We had, we were able to identify the methyl thiol radical, which is this bond association, and showed this to be the major channel in dimethyl disulfide with about a 30% CS bond association coming mainly from multiphoton absorption. The second point we made was that, in fact, X-ray absorption spectroscopy in the hard X-ray region, so at a free electron laser above 7 keV or so, will always have these pre-edge features, and these are features that are dipole forbidden and these are quadrupole allowed. So these are some ferrocene molecules which I'm thinking about more and more lately, and what you see here are 1s to D type transitions that occur because of the breakdown of the dipole approximation at the hard X-ray limit above 5 keV. So indeed, we think that X-ray absorption spectroscopy, not just at the carbon KH, but utilizing the broadband, the tunability, and the access to multiple absorption edges could be a universal probe of molecular dynamics. What I've shown today are 3 reactions mapping chemical dynamics at the carbon KH. The first 2 were ultrafast ring opening reactions of pure hydrocarbon, where we showed the mixed 2 pi 1 pi star nature of the molecule in the vicinity of the pericyclic minimum. For perfural, we showed the 2p orbital 1s to 2p resonance at the carbon KH. And finally, for acetalacetone, we showed a time delayed signature close to about a 2 picosecond, which is one of the fastest known ultrafast intersystem crossing in a molecule. So with that, I'd like to thank again my former postdoc advisor, former group in UC Berkeley, DOE, NSF for the funding, current colleagues at the University of Iowa who have extended a lot of support to me at a very difficult time, and Jerry, once again, for inviting me for this talk. Thank you very much.
Wonderful talk. We'll do one last question. Your lab in Iowa. So are you going to be setting up ultrafast X-ray and ultrafast optical? What will you have in-house, and what facilities do you plan to go to support your research program?
Yeah, thank you for that question, Jerry. I imagine that might come up. So this is one of the first experiments that I'm hoping to do in my lab in Iowa. This is going to be a metallocene, which is why I ended with the ferrocene slide. It's something I'm starting to think about lately. And metallocenes are of interest to me because these are, metal transition metal active sites which can grow polymer chains. And so one of the first experiments that I want to do is photoexcite this molecule and look at the oxidation state changes that people have studied in general for transition metal complexes. This is the active site, and we will be doing soft X-ray absorption again, or extreme ultraviolet in this case, to look at the oxidation state changes in the metal. And in the longer run, what I'm interested is to look at the changing sort of the bond covalency of the metal halogen as well as the metal carbons at the carbon KH as well as the halogen M and N edges to get sort of a multi-elemental viewpoint of this. The first few years is definitely going to be ultrafast X-ray, and that's going to, I'm pretty sure, keep me on my toes for the next 3 to 4 years. Going forward, I also have experience with optical. I would be interested in looking at some 2D electronic spectroscopies in the longer run.